Welcome back to G Fun Facts Online, where we peel back the layers of the ordinary to reveal the extraordinary science happening right under our noses. Today, we are going to take a journey into the invisible infrastructure of our future. We are talking about the internet, but not the websites or apps you use. We are talking about the physical waves that carry your data through the air. You might not realize it, but we are currently standing on a precipice. For decades, the digital economy has been traveling on simple waves, radio frequencies like 4G and 5G, or pulses of light in fiber optic cables. We have largely relied on a method that is surprisingly primitive. Think about it. We modulate the amplitude or the frequency of a wave. It is akin to sending Morse code by flicking a flashlight on and off. It works. It is effective. But compared to what the laws of physics actually allow, it is incredibly basic. And here is the problem. The old methods are hitting a wall. The demand for bandwidth is insatiable, doubling roughly every 18 months. We are literally running out of colors of light and frequencies of radio to use. But, and this is where today's story begins, nature has hidden a loophole in the mathematics of light. It is a loophole that researchers have only recently learned to exploit. It involves twisting light not just into a spiral, but into a complex knot-like structure that is mathematically indestructible. Today, we are exploring the Skyrmion Vortex. This is not just a faster way to blink a light. It is a fundamentally different state of electromagnetic radiation. By manipulating the topology of light, scientists have created hurricanes of energy that can weather the chaotic storms of atmospheric turbulence that kill standard 6G signals. This episode is going to take us from the abstract particle physics of the 1960s all the way to the cutting-edge metasurfaces of 2026. We are going to see how a donut-shaped knot of energy might just be the key to the terabit-per-second speeds of the future. To really understand why this is a revolution, we first need to look at what came before it and why it failed. For the last 2 decades, optical engineers have been absolutely fascinated by something called orbital angular momentum, or OAM. If you imagine a standard laser beam, it moves forward like a bullet. But an OAM beam spins like a drill bit. The wavefront of this light forms a helix, a corkscrew shape. If you were to slice this beam in half and look at the cross-section, you wouldn't see a bright dot in the middle. You would see a ring, a vortex of darkness surrounded by light. This vortex beam allows for a technique called mode division multiplexing. Essentially, you can send a beam with one twist, let us call it mode +1, another with 2 twists, mode +2, and another with a reverse twist, mode -1, all down the same channel at the exact same time. It is like having multiple independent conversations in the same room, but each conversation is happening in a different pitch of spiral. It sounds perfect, right? Infinite bandwidth. But OAM beams have a fatal flaw. They are fragile. When an OAM beam travels through the open air, which 6G signals must do to connect base stations to your phone, it encounters phase noise. Turbulence, humidity, rain, and even dust particles distort the wavefront. A beam launched as mode +1 might arrive at the receiver looking like a messy mix of mode 0 and mode +2. The corkscrew unravels, and the data is corrupted. This is where the concept of topology comes in to save the day. You might have heard of topology described as rubber sheet geometry. To a topologist, a coffee mug and a donut are the same object. Why? Because you can stretch the mug into the shape of a donut without tearing it. They both have exactly one hole. This number of holes is called a topological invariant. No matter how much you squish or stretch the object, as long as you do not tear it, the number of holes stays the same. Now apply this to physics. The Skyrmion is a topological feature. It was originally proposed way back in 1961 by a British physicist named Tony Skyrmi. He was trying to explain the stability of subatomic particles. Later, this concept was adopted by condensed matter physicists to describe swirling patterns of magnetic spins in exotic materials. But in recent years, this concept leaped from matter to light. An optical Skyrmion is not a particle of matter. It is a pulse of light where the electric and magnetic field vectors twist in a complex, 3D pattern that mimics the mathematical structure of Skyrmi's particles. Unlike a simple OAM corkscrew beam, which relies on a fragile phase structure, an optical Skyrmion's identity is locked into the relationship between its polarization, which is the direction the light waves wiggle, and its spatial structure. This complex texture forms a knot, and just like the donut, this knot is robust against perturbations. You can distort a Skyrmion beam, stretch it, squash it, pass it through turbulent air, and the knot remains tied. The receiver can look at the messy beam, calculate its Skyrmion number, which creates an integer like +1 or -1, and retrieve the data with near-perfect accuracy. While the theory of optical Skyrmions has been building for a decade, a practical device for 6G communications remained elusive until early 2026. A collaborative team led by Sueqian Zhang at Tianjin University, working with researchers from Nanyang Technological University, published a landmark study in the journal Optica that changed the game. The challenge they faced was simple. To use Skyrmions for data, you need to be able to switch them. You need to turn a Skyrmion A into a Skyrmion B rapidly to represent the ones and zeros of digital binary code. Previous methods were slow and static. The Tianjin team solved this using a non-linear metasurface. A metasurface is a 2D material engineered at the nanoscale. Imagine a city for ants, consisting of an array of tiny antennas, specifically gold split-ring resonators, that are smaller than the wavelength of light they interact with. When light hits these resonators, they don't just reflect it, they reshape it. This breakthrough device works in the terahertz frequency range. This is the Goldilocks zone for 6G. It is higher frequency than 5G, but lower than visible light. Terahertz waves can carry massive amounts of data, potentially terabits per second, but they are notoriously difficult to control.